We'll start recording a new one, just in case, but I don't want to duplicate on that. So we've got our unimolecular reaction with all those individual things to worry about. Okay. If we looked at the rate for the unimolecular reaction, what would our rate law be? Rate equals K times our substrate. Just like, that says substrate. Whatever. Okay, just like our SN1 reactions. Okay. What did I just pop up with now? Okay. What if the alkene produced had less than 3 hydrogens? So this is an interesting question. What are we talking about here? So in our product, we've got 3 hydrogens on that product. What if instead of that being our situation, whoops, come back here. Because I yelled at it. What if we had something like this? Less than 3 hydrogens. So now there's only 2 hydrogens on there, right? Could that potentially change the product? Is there another way I could orient all of these atoms, but still maintain the same atom connectivity, but not be superimposable? What's the problem with that? There are 2 possible products when we run this elimination reaction. Okay, what is the relationship between these 2 structures? What are they? There are structural isomers, or our constitutional isomers. And then another group of you came out with our other definition. We've got a trans arrangement and a cis arrangement. To determine that, what we went through and did was evaluated our highest priority groups, the carbons, and we looked to see where they where they were located around the double bond. So in our cis case, they're on the same side of the double bond. In our trans case, they're on opposite sides. So when we go through and run an elimination reaction, we have this issue popping up. Okay, so we'll need to talk about kind of the nomenclature on this. So we're not going to get into alkene nomenclature per se. We'll save that for after exam 3, but we do need to talk about the relationship between our products. So this is our cis-trans issue. Cis-trans really only works as a relationship or a definition between any 2 groups. But what if you have more than 2 groups? Okay, well, then it doesn't work, because cis and trans only apply to 2 groups. All right, so when we think back to our ring structures, we looked at our rings, we only picked 2 atoms, and we said, where were they relative to each other around the ring? Okay. But when we moved to a double bond, we could envision structures like, say, maybe this guy, or this one, that have more than 2 things attached to them. In fact, that second one, let me highlight the double bond. That double bond now has absolutely no hydrogens attached to it. So really, we have to look at the orientation of 4 different groups. So cis and trans becomes a little bit awkward to deal with as far as nomenclature goes. So what we come up with is, instead of using cis and trans, we use another terminology as Z and E. What that's going to do is define the absolute relationship around a double bond. Okay? It's really only going to apply to things that have less than 2 hydrogens, though we can... Sorry, no, that's right, less than 2 hydrogens. Because in any other circumstance, if we have 3 hydrogens, there isn't 2 big groups around that double bond. And there's 4 hydrogens, there's no big groups. So there's no point of defining it. So when we look at our cis-trans, we can pick any 2 groups and we can say they're cis or trans relative to each other. But it's not an absolute relationship. We're just picking arbitrarily what we want to look at. Okay? So if I asked you, what's the relationship between these 2 hydrogens in blue? They are cis because they're on the same side of the double bond. But if I now ask, now I'm going to have to pick the proper structure. This guy, what is the absolute configuration of that double bond? cis and trans only applies to two groups. In this case, we do have two groups, so we could probably sneak out using the cis-trans moniker. But we want to get to an absolute configuration. That absolute configuration is our ZE definition. Okay, so to go through and decide whether it's Z or E, it's going to be kind of similar to what we did for our R and S systems. So we're going to look at our priorities. So the first thing we'll do is cut the double bond perpendicular to its axis. When I say perpendicular, I'm talking about right through here. Okay. And now I'm going to look at each half, and I'm going to star the side that has the highest priority. So let's take a look at the rightmost half. We have two things attached. CH3 versus hydrogen. Which has higher priority? CH3. Why? How do we assign priorities? The atomic mass, just like we did for R and S. Carbon has a bigger atomic mass than hydrogen, so it gets our star. We move to the other half, and now do the same thing with it. Where's our star go? With our carbon. Now what we can do is cut the bond, double bond, parallel to the axis, which is running right through the middle. Where are our stars? Same side or opposite side of that line? They're on opposite sides. If they're on the opposite side, we will call it E. Okay? We could define this one as trans, like I said, because we only had two groups. Okay? What about if they were on the same side? We just call it Z. How do we decide or remember those two things? There are two options. We'll start with the one that I'll stick with, and then we'll stick with another one that a student suggested. With our cis and Z, cis means what? Same side. Okay, so the other way you could look at it is Z is that they are on the same side. Okay, it works. Z, same side. Okay. So look to where your stars are. If they're on the same side, there's cis or Z. How do we get the opposite sides? The other one is how I remembered it for the longest time. I think it was a couple semesters ago that another student shouted out in the middle of the class, "Oh, it's just tranny." I don't know why, but for some reason that helps them. So tranny for trans and E being the same. Okay? Those two terms are now perfectly aligned with each other. Okay? I don't want to go into any more details than I have to on that one. So what happens? Let's take a look at one more example before we quit this, because we really only have time for one more example. What happens if we have two double bonds? You will have to label both double bonds. Okay, so let's start with the top one. What do you think? It's cis, which means Z. How about the bottom one? Wow, did you guys really figure that one out that fast?
I did it earlier while you were talking.
Go in half first. Bromine versus carbon. Bromine. Go to the other side. Carbon versus carbon. No difference. This one we could kind of cheat and just go out and see that we had more carbons up top. But officially you would have to break that down into your phantom carbon. Okay. Which you don't have to remember that necessarily, but it does potentially show up. So that top one has the higher priority. What's the relationship between our purple stars? They are on opposite sides of the double bond. We cannot specify this one as trans. Why? There's
two sections.
We have, it's our two hydrogen rule. Okay, we don't have any hydrogens around that double bond. It must be specified according to our ZE moniker. And in that case, they're on opposite sides. We're looking at E. Thank you for your patience through the middle.